This webcast looks at Worksheet 3C, where we are talking about stacks of kinematic graphs. The kinematic graphs are the graphs that help us visualize the motion of an object. They are the position versus time, velocity versus time, and acceleration versus time graphs, and we tend to stack them, as you can see on the left here of the worksheet. The reason that we do that is because the time axis is the same on each of the graphs, and by stacking them we can see how all of these aspects of the motion are changing and how they connect. And also there's another reason that we tend to stack these graphs. The position versus time graph, the way that we find velocity is by taking the slope of the position. So this velocity versus time graph is showing the slope of the graph above it. And when we have velocity versus time, the way that we find acceleration is by looking at the slope. And so the acceleration versus time is showing the slope of the graph above it. So each one of these is showing the slope of the graph above it. Okay. On this worksheet, for this drawing or scenario at the top of the page, we are going to use the stack of kinematic graphs on the left, and at the bottom of the page we have a scenario number 2, and for it we are going to use the stack of graphs along the right hand side of the page. Okay, let's look at the first scenario. So here we have a ball which is initially at the top of this ramp, and it is going to be allowed to roll down the ramp. It's at rest at the top of this ramp. And I can tell from the positions that they have labeled that as it moves down the ramp, the ball is moving in the positive direction. So actually, this is quite similar to the lab that we just completed, which was the cart on an inclined ramp. Well, this is a ball on an inclined ramp. Okay, so the first thing I'm going to do is to draw a motion map, and I'm going to use this ramp as the place where I draw the motion map. And so I'm going to show the velocity vectors above the ramp, and I'm going to show the acceleration vectors below the ramp. Okay, but first I'm going to put my position dots to show where the ball is as each second passes. Now the ball starts from rest, and so it does not move very far in the first second, but as each second goes by it moves faster, and so the distance between the dots gets longer and longer as it moves down the ramp. And I'm going to put the velocity vectors. They are pointing in the direction that the ball is moving, which is down the ramp. And I see my velocity vectors getting longer because the speed is increasing. Now let me go back and show the acceleration vectors. Now I put the position dots in exactly the same place that they were, right, because the position is the same, but I'm just putting them again so that I can show the acceleration vectors. The acceleration vectors point in the direction that speed is changing. And in this case, and they also point in the direction of the net force. Now, the reason that the ball rolls down the ramp is that there's a force of gravity that pulls it down, and the force of gravity is pulling it down to the ground, and so that force is pointing down the ramp, and so that's the same direction that the acceleration vectors are pointing. Also, I know that we've learned that when an object is speeding up, the acceleration vectors point in the same direction as the velocity vectors, and that's the case here. This ball is speeding up. Notice that I made my acceleration vectors all the same length because we're talking about situations with uniform acceleration. So the velocity is changing, it's getting bigger, but the acceleration is not. The acceleration is constant. Okay, so that was just a review of putting my motion map. Now I'm going to show the kinematic graphs for this scenario. So it begins at a position of 0, and as time goes on, its position is increasing, but because it's accelerating, so it's going to end up here, I guess, but as it's accelerating, this position versus time graph is not linear. It is curved, and the slope needs to get steeper and steeper as time goes on. So it's a parabolic curve. That's the shape of a position versus time graph when it is accelerating. Now, the velocity started at 0, right? Because this ball was at rest at the top of the ramp, so its velocity was initially 0, but the velocity became a larger and larger positive number because the ball was moving in a positive direction and speeding up. Well, sorry girls, you know sometimes on one note. There we go. So I have a linear velocity versus time graph, and notice that all my velocities are positive because it's always moving in the positive direction, and they're getting bigger. The acceleration is constant, and the acceleration points in a positive direction. The acceleration is the slope of this velocity versus time graph. So my acceleration should be a horizontal line at some positive value. Okay, so we have just made a stack of kinematic graphs for that scenario. Let's go on to the next scenario. Okay, so here I have a ball that's going to get pushed up a ramp, and notice that here at this position the ramp becomes horizontal. I can see that the ball is moving in the positive direction because it's going from 0 centimeters to 50 centimeters. I'm going to assume a constant velocity where the ramp is horizontal. Okay, so let me do a quick motion map. Now, the ball gets pushed up the ramp, and so when the hand or whatever applies that force, it initially goes very fast, and then it slows down as it moves up the ramp. So as it goes up the ramp, I initially see a very long velocity vector, and then the velocity vectors get shorter because it is slowing down as it moves up the ramp. But on this horizontal section of the ramp, it is moving at a constant velocity, and so those position dots are evenly spaced up there. So this is the velocity portion of my motion map. Now I'm going to show the acceleration portion, and I'm going to put those position dots in exactly the same places. Okay, for the portion of this trip when the ball is going up the ramp, the ball is slowing down, and I know that when velocity is decreasing, the acceleration vectors must point in the opposite direction of velocity. Also, I could think the gravitational force is trying to pull the ball back down the ramp. So the force of gravity is pulling it down, and that is the direction of the acceleration along this inclined portion of the ramp. When we get to the horizontal portion of the ramp, the velocity is not changing. Acceleration is 0. And so I don't have any acceleration vectors for this horizontal portion. Here, I only have the position dots. Acceleration is 0. Okay, so let's go do our stack of kinematic graphs. So here, it started at a position of 0, and it slowed down as it moved to a higher position. So since it's moving in a positive direction but slowing down, I should see the slope getting less steep. So I have a parabola, but it's shaped this way, where it starts out steep and then gets less steep. And then, for the next part of the trip, it's moving at a constant velocity in the positive direction. So I've just got a line moving in the positive direction. I'm just going to put a dashed line here to denote that point of time where the ramp changed from being slanted upward to being horizontal, just so that I can compare across these graphs what happens at that point in time. Okay, so I have the position versus time graph. Now I'm going to show the velocity versus time graph. So it started at a big velocity, right? Someone pushed that ball up the ramp, but it gradually got slower. And so I see the velocity becoming smaller, and it's changing at a constant rate. And then when we get to the horizontal portion of the ramp, the velocity is constant. It's still moving in the positive direction, so it's a positive velocity, but it is now my velocity versus time graph becomes a horizontal line. For the acceleration versus time, this graph should show the slope of the position versus time graph above. And so in this first portion of the velocity versus time graph, I have a line with a negative slope. Acceleration is negative. Remember, we drew the acceleration arrows, the vectors, going in the negative direction. And then for the second portion of the trip, the velocity is constant, so it's a horizontal line, and the slope of a horizontal line is 0. It is not accelerating for that second part of the trip, and so the acceleration jumps to a value of 0. Notice that I have a disconnect here in my acceleration versus time graph, and that's just fine. Okay, and let's go do number 3 and 4, which are along this similar thing. Here we have a ball. It's at the top of a ramp, and it's going to roll down the ramp. I notice that it is going in the positive direction, even though, as I look at it, it's moving to the left, but the way that they have set up the coordinate system, it's moving from 0 to a larger position. And there's a very important point here, right here, where the ramp inclination angle changes. Here, it has this kind of inclination angle, and then for the lower part of the ramp, the inclination angle gets a lot bigger. Okay, so it gets steeper for the second portion of the ramp. Okay, so let's do a motion map. I'm going to show velocity vectors first. It begins from rest, and so it's not going very fast in that first second, and then it gets faster and faster. So it speeds up as it goes down the ramp. And then here at 25 centimeters, the ramp gets steeper, and so it starts speeding up even faster. And I don't really have maybe enough space to show it, so I'm just going to show one big velocity vector there, but it starts to speed up even faster. And now let me go back and put the acceleration vectors. Now the force of gravity is pulling the ball down the ramp, and the acceleration is in that direction of that net force, but also it's speeding up, and so I know that the acceleration points in the same direction as velocity when it's speeding up. These first 3 acceleration vectors are for the first part of the ramp, when we've got a small inclination angle. But when we get to the next part of the ramp where the inclination angle is steeper, the acceleration gets bigger. So this is maybe one of the few times when I'm actually going to see a change in the amount of the acceleration. Okay, so let's go show the kinematic graphs for this situation. The position starts at position 0, and then it gets, to a bigger position, and then an even bigger position. And as it moves to these, from one position to another, it's moving with increasing speed. And so the shape should be parabolic. And I'm going to take out this dot just because it's hard to draw this. So I've got this shape of parabola. For the bottom portion of the ramp, it's still parabolic, but it's at a steeper shape. So the lower portion of this parabola is kind of like a champagne, or I don't know, a wide goblet. And the upper portion is kind of like a champagne flute. So I'm trying to change the shape of the parabola. That's very difficult to draw. So, but anyway, that's what I had in mind. Now the velocity, it moves. It's getting faster at one rate for the first part of the trip, and then it gets faster at a steeper or a faster rate for the second part. I could put a dashed line here just to show the point where the inclination angle of the ramp changes. The acceleration is one level for the first part of the trip, and the acceleration increases for the second part of the trip, because the acceleration is the slope of the velocity versus time graph above it. The slope for the first part of the trip is not quite as big as the slope for the second part of the trip. Okay, and then the final one here is number 4. We've got a ball that's going to roll up the ramp and then roll back down. And so someone gives it a push, and so it has a very fast speed at the beginning, and then gradually slows down as it moves up the ramp. So I see the velocity vectors going up the ramp and slowing down, but it reaches a certain point and then it turns around and it begins moving back in the other direction. So now my velocity vectors have changed direction, and I see them getting longer as it speeds up on the way down. Then I'll show the acceleration vectors. So first I'm going to put in the position dots at the same places. So as it's moving up the ramp, the force of gravity is trying to pull it down. So that's the direction of the acceleration vectors. And then on the trip down, the force is still trying to pull it down the ramp. And so the acceleration vectors always point down the ramp, which, by the way, is the negative direction, right? Because as the ball goes up the ramp, it's moving in the positive direction. Okay, so let's show this in the kinematic graphs. So it begins at a position of 0, and I'm going to show a dotted line just to represent where the ball turns around and begins moving back in the negative direction. So first it's moving in the positive direction but slowing down. So it's parabolic and the curve is getting flatter. And then it reaches the peak height, and then it starts going back down the ramp and it speeds up. And so it's parabolic and the slope gets steeper. So that's the shape of the position versus time graph. The velocity started at a big positive velocity. Someone pushed that ball up the ramp. When it reaches this peak of its height, it actually, for an instant, has a velocity of 0. In the process of just as it's ready to turn around, the velocity is 0, and then it speeds back up in the positive direction. Oh, I'm sorry, it speeds up in the negative direction. And so the velocity looks like this. It starts out fast in the positive direction, it slows down to 0, and then it speeds up to the negative direction. The acceleration is a constant, and it's always negative. And I can see that the slope of my velocity versus time is constant and negative.